Matt from 2011, just going to do the first 10 multiple choice questions. Here's the first one, very easy. You've got a y-intercept of 1, which immediately discounts this graph. You've got a positive cubic, so it starts over here, ends up here, so we can discount this graph. And then what's the key difference between this one and this one? Well, this one has a root at 1 and this one doesn't. So we just assess what happens when x is 1. Put in x as 1, you get y as 0. So it does have a root at x is 1, and so the answer is C. Very easy warm-up. Good. This question talks about what must be true. So we could put our Tamua brains on it for a second if we wanted to and just think about counterexamples. So for example, here's a rectangle. Don't tell me that's a square. It's a rectangle. Perimeter 4, area 1. And which of these is immediately discounted? Well, area squared as 1 is not bigger than 9, so that goes away. 1 times 4 is 4, which is not bigger or equal to 1 plus 4, which is 5, so that goes away as well. So this counterexample did a good job there. It doesn't work for this because 64 is bigger than 1, and it also doesn't work for this because 16 is equal to 16. So okay, we're down with these two. And I'll give you a second. This really tests how good you are at counterexamples. I'll tell you the answer. The answer is C. This is the true one. Can you find a counterexample for this? It's not that easy to find, but the hint is you're going to cube something and you're going to aim to make it very small. What numbers, when you cube them, become very small? Well, negatives do, but you can't have a negative perimeter. The other thing that does is very small numbers between 0 and 1. When you cube things between 0 and 1, they get smaller, right? Not bigger. So if I use a very small side length like this, the area is 0.001 because you just move the decimal point back a couple more times. The perimeter is 0.04, which when I cube, 4 cubed is 64, but move the decimal point back 6 places, 1, 2, 3, 4, 5, 6, hope I got that right, and we get a perimeter cubed less than the area. So that one's not true by counterexample. Of course, you can prove that this one is true if you just get out a regular rectangle with x and y and have this, and then you can say the perimeter squared is this, which is this. 16 times the area is that. You can obviously say you put this one and then this one here, take away 16xy, factorize or divide by 4 first, then factorize, and of course this is always true. Now this is not a proof of this, I should just say for the side. To actually prove this, you start here and work backwards until you get to here. But of course I know all these steps are reversible, so it will work as long as I write it in the right order next time. But yeah, the answer is definitely C. This question, kind of interesting. Here's a cubic. Essentially, there's a cubic. It's not a true graph because we're only interested in kind of integer n inputs. So it's a sequence, right? You use n is 1 and put 1 in. You put n is 2 in, and you get the next value when you put 2 in, and so on. So it's not a true graph, but we can kind of treat it as one. We know cubics kind of end here and here, as we said before. It's got a y-intercept of 631, so it looks a bit like this. And all I'm being asked here is, for what's the largest value of n for which a term before the next term is bigger? So in other words, like if we take a value over here, like x10, x10 is bigger than x9. So the next term is bigger than the one before it. It's asking me for the reverse. It's asking me for when the previous term is bigger than next term, and when's the last time that happens. So essentially what I'm looking for is somewhere in here, where like if this was the value of x3, and this was x4. x3 is bigger than x4 because it's higher up in the graph. And I'm being asked what's the last value that does that? Well, of course, because it's a cubic, it heads off to infinity this way. So there'll be a last value before you hit this turning point. So all I need to do is look for the turning point of this graph here if I just pretend it's a graph. So to differentiate, of course, this is very easy to solve now. When I set it to 0, I get solutions at 0 and 6. And so this turning point is at 6, which means that, and the other turning point is at 0, kind of interestingly, which means that the last value to be bigger than the one before it, the last value to be bigger than the one after it is x to the 5. Right? x5 is bigger than x6, because 6 is the turning point, and then x7 is bigger than x6. So x5 is the last value to be bigger than the one after it, and that would be my answer there, which I can just do. D, kind of interesting as well, so let's get out the sine graph, of course, immediately, because, when is sine greater than a half? Well, we should know that sine of x is a half, has a solution at pi over 6, and then by symmetry, pi minus pi over 6 gives us 5 pi over 6 as the other solution. So we need to be in here. That's the range here, which is above 0.5. Now, sine of 2x is, of course, the graph squashed in by factor 2, so it does 2 of these peaks before returning to 2 pi. But of course that means that this value is halved, and so is this one. So this is now going to have a range being greater than a half between 0.25, what am I talking about? This is pi over 6, so half that is pi over 12, and this is 5 pi over 6, so half that is 5 pi over 12. So that's going to have a solution here, but also this value, which is pi over 6 plus 2 pi, and the next value after it, those are also going to be halved down and going to be within the range. So I can take, if I add 2 pi to that, I get 13 pi over 6. If I add 2 pi to that, that's going to be this corresponding solution here. Halve them down because this graph squashes everything in by factor 2 to get 13 pi over 12 and 17 pi over 12. And you can draw the graph if you want to make that easier, but I was talking about these solutions here, which are half of this value here, 13 pi over 6 halved to make 13 pi over 12, just bigger than pi. So okay, those are my 3 ranges that I can use, and I'm allowed to have either one or both of these things true. Now this range is clearly living on its own, so that's good. Now these 2 ranges interfere with each other a little bit, like this range here and this range here share some inputs, but not all of them. This is the range that kind of just lives on its own, so I can just kind of take that for later. But here, what's the total sum of these? Well, the lowest bit is pi over 12, right? And then this range is true all the way to 5 pi over 12. But 5 pi over 12 is it's still being, this graph is still being true for that for this thing up here. This graph is true all the way to 5 pi over 6. So actually, combining these, and not combining them for when they intersect, but just combining the union of them, we can just take the lowest bit here and the highest bit there, and we can get all of that. So it's true from this point here all the way to that point here, and then also true for this thing here, which, as I said, is living on its own. So okay, so essentially, how much of the 2 pi domain, what fraction is all of this? So let's look for the length of this range here. So it's just 5 over 6 minus 1 over 12. I'm ignoring the pi's because I can't be bothered to deal with them. Double that to make 10, take away 1 is 9. That's 3/4. And then this one here, do this, take away this, just to get 4/12, which is 1/3. And so in total, I have 3/4 plus 1/3 pi, I should really say, which I'll say in a second. So I've got 13 over pi of the total 2 pi range is the sum of the 2 ranges. And 13 over pi of the total of 2 pi, or sorry, 13 over 12 pi of the total 2 pi. So just divide this by 2 pi and you get 13 over 24 is our fraction over the whole domain for it is true. So E then, I don't know why this seems so natural to me, but it seems incredibly natural for me to draw this in with a 90-degree angle there. That seemed like the most natural thing in the world. I then called the radius of the circle 1, just because why not? So I called the radius 1, and then I could call this length here, if I label this point A, this length is AC, and so sine of A is equal to 1 over AC, just using opposite over hypotenuse. But of course I can rearrange that to get AC as 1 over sine A. So this length is 1 over sine A, and this length is also 1, right, because it's also a radius of the circle. But now I can just use sine rule. I can say 1 over sine beta, I think I called it, did I call that an alpha? I should have called it, I think, yeah, anyway. 1 over sine beta is equal to AC over sine gamma, but AC is 1 over sine alpha, so I get this via sine rule. 1 over sine beta is 1 over sine alpha, which is AC, over sine gamma. Of course, this just goes down to there to make this, and now sine beta must equal sine alpha sine gamma, which is condition number 2. Kind of an interesting question. F. So we need to complete the square on this to make a circle, so we halve this down. Cos theta is just a constant. I mean, as long as you choose theta, obviously, which is just some number here, this is just a constant. So you halve this number down to get 2 cos theta, and put that in a bracket with x, and then you take away the square of this, so take away 4 cos squared. Do the same with this, so halve that down to make 4 sine theta, and then take away the square of that, and then you just drop the 10, and now we can move all of these constants over to the other side, here, and we can collect. I wrote 16 sine squared as 4 sine squared plus 12 sine squared, and I did that because now I can collect these two things together to make 4 into cos squared plus sine squared, because I know that's just 1. So this whole thing makes 4 minus 10 is minus 6, and we get this. Now, again, whatever value I choose theta, this is just a number, and so is this. So the center of the circle is defined as long as I just choose some theta to make these some numbers. Now here, this is equal to the r squared, right? But if this is equal to r squared, then I'm going to need this to be bigger than 0. Sorry, is this equal to r squared? Yeah, it is. yeah, I need this to be bigger than 0. If this was negative, then r squared would be a negative, and I can't have that. So this must be bigger than 0 for this graph to have some radius that exists. So I just need that to be bigger than 0, which I can of course rearrange to this. And now, usually when you square root here, you have to be careful of the inequality, but we're only in this range. And if you look at the sine graph, sine is always positive in that range. So actually I can square the root this without any fear at all, because sine is just never negative in this range. So I just need sine to be bigger than 1 over root 2. You've probably typed that into a calculator enough times to know it's about 0.7. And you also should know that the critical value there is at pi over 4. Right? And also, on the other side, 3 pi over 4. It's pretty clearly this one just from the picture, though, because none of the others have any bearing. So you actually could have gotten away with not knowing the exact values there, but you should do anyway. And the answer is B. So this question I'm very confused about. I'm going to do it the way that I did it, and then because I'm not sure that the way that I did it wasn't a complete fluke, I'm going to do it in the way that the work solution did it. The way that I did it was I defined f as a piecewise function. I said between -1 and 0, it's clearly the graph x plus 1, and so that's what this is. And between 0 and 1, it's clearly the graph 1 minus x, and it's just the graph 0 otherwise. So this is called a piecewise function. They're fairly self-explanatory. It's just it behaves as this function in this part, it behaves as this function in this part, and it behaves as this function everywhere else. And then what I did is I just replaced the x with an x squared. So if you just replace this input with an x squared, you just replace these inputs with x squareds. And now, why have I changed this one so much? So clearly I just changed this to an x squared. Why did I change this one so much? Why isn't it just x squared plus 1? Well, the thing is, when you put in x squared, like imagine if you're substituting in minus 0.5. Minus 0.5 squared is positive a quarter. So actually, any input between 0 and -1 behaves the same as its positive counterpart, because when you square it, you get a positive number. So whatever the graph was doing in the positive section, it must also now be doing in the negative section, which is why I've written it as this. And the graph should look a bit like this. This is just the graph of 1 minus x squared. Right? So okay, I've done that. Now I'm just going to take away 1. From the x value here, and I absolutely don't know if I'm allowed to do this. This is a problem. So I read this as just shift it across one place to the right, which just creates this graph, of course with turning point of 1, 1, which just creates this graph. And again, it's 0 outside, and I've changed the ranges as well to be between 1 and 2 and 0 and 1, because the whole thing is shifted one place to the right. And now, when I'm doing the integral of this function between -1 and 1, well, the integral is, the function is just 0 here, right? I haven't drawn the horizontal lines, but it's just 0 here. So all I need to do is integrate this function between 0 and 1, and that function is this thing here. Of course, I can expand that out, and stuff cancels, and when I do the integration, I get the answer of 2/3. Now, I have no idea whether that's a fluke. Essentially, graph transformations goes really wrong when you do more than one transformation sometimes, and I've written to 3blue1brown asking him to make a video about it. But I've long come to the conclusion that I'm not good enough at either maths or making videos to tackle that problem myself. So I have no idea whether this is a fluke or not, honestly. But okay, let's just do it the work solution way anyway. But what the work solution said is that x is essentially just between -1 and 1, because if it's outside that, the function is just 0, and so not worth thinking about. Now, if you're going to input this thing instead, we'll square everything to get x squared is between... Firstly, you could just square that to get 1 and say x squared is between 1 and 1, but that doesn't make any sense. X squared is between 1 and 0, because anything that you square between -1 and 1 is just going to be something between 0 and 1. Then you take away 1 to get this as the range. So essentially, for any x value in this range that you put into here, you're going to have an answer in between these two things. So what the work solutions are arguing is that this function, you basically may as well only consider this part of it. Because anything that you input, for any x value that's worth inputting, you're just going to get a value between -1 and 0, thus the function is going to behave like this. So this function, which I've already said is x plus 1, is the only function that's worth thinking about. And now they've just substituted an x minus 1 into this input to make this, and said that's just that. And now we can just integrate that between 1 and -1. As it tells us to do, and we get the answer of 2/3. So again, the answers match. I don't know whether it's a fluke, but yeah, that's how they did it. H, going back to maths that I actually understand properly, this is 2 cubed, this is 3 squared, this is 2 squared, and this is 2 because 0.5 squared is 0.25. So we can put all that down straight away. We multiply indices in this law here, so just doing that a few times. We now have power law of logs, whereby this 3 can jump up to here, and this 2 up to here, and this 2 up to here as well. And now 2 to the log 2 just all cancels, and this whole thing is just x cubed. And this whole thing is x squared, this whole thing is x squared as well, and then this. And then we can tidy that up for this. And now we just have a cubic to solve. And we're only interested in positive values of this cubic that's solved. So we know this is a cubic, we know it starts over here, ends up here. It also has a y-intercept of 2. And so it must have a negative solution to get from here to here, but we're not interested in that. What we're interested in is, does it have any positive solutions over here? Does it turn back hard enough to have any positive solutions? If so, how many? And there's a few ways you could do that. You could differentiate and find the turning points and then assess where they were. It's actually easier just to notice if you substitute 1 into here, you get 0. So by factor theorem, x is 1 is the solution, and you can factorize out an x minus 1 term. And again, polynomial division if you want to, but I never do polynomial division. I always just write out the x minus 1 out here and then just spot the factorization. Now this must be a 1x squared because x times x squared makes x cubed. This must be a minus 2 because minus 2 times minus 1 is plus 2. And I just need this term in here. But of course I can just look at maybe this term here. Minus 1 over here must equal minus a minus 2. That's where the x's are coming from. So I've got minus 1x over here. I've got minus a of them and minus 2 of them over here. So they must be equal. A is minus 1, and you get this, and that factorizes to this. And so you actually have a solution at 1, a solution at 2. Again, you can check factor theorem to make sure that works there, which it hopefully does. And a solution at minus 1, which you don't care about. So there are 2 positive solutions that we actually care about. Good. So we're going to use some more factor theorem here, I think, eventually. Now, I immediately thought of this rule here for this question. And then what I decided to do was say that cos to the power 6 is cos squared times cos squared times cos squared, which is 1 minus sine squared times 1 minus sine squared times 1 minus sine squared. And then I expanded all of that out because I'm a complete madman and just had no regard for human life, my own life really. Now I can write sine as s and say this is this. I don't even know what this is called. It's a polynomial of degree 8. I don't know what the name for that is. And now essentially I'm looking for solutions to this. Now clearly there is a solution at s is equal to 0, which means sine is equal to 0, which gives me 2 solutions at 0 and pi. Not 2 pi because that's not included, but I get 2 solutions at 0 pi. We can clarify that, right? Sine of pi is 0. Sorry, let's just do, that should be a singular pi. Apologies. I'll just change that really quickly. And then just run back to it. So sine of pi is 0, so that's 0. Cos of pi is minus 1. Minus 1 to the power 6 is positive 1, so this works, and likewise for 0. And now I can divide this by s squared to make this function, and I can look for this. I can see whether there are any more solutions to this. Now I can notice, again using factor theorem, that 1 and minus 1 are both solutions to this, because 1 minus 1 plus 3 minus 3 is a solution, and if you put in minus 1, because these are all even powers, you're going to get a solution as well. So that's nice. Sine of 1 is a solution, which gives you x is pi over 2, and also sine of minus 1, which gives you x is 3 pi over 2. Again, draw the sine graph just to help you out with those. So those are 4 solutions so far, and now I just need to assess, does this have any more solutions outside of the plus and minus 1? So let's have a look at it. Well, I can factor out the plus and minus 1. And then again, you can do polynomial division with this and then this, or you can just multiply these together and then try and spot the factorization. I already know this needs to be a 1s to the 4, because otherwise I'm not going to get a 1s to the 6. And I know that must be a plus 3, because 1 times minus 1 is minus 1, times plus 3 is minus 3. And now I can just spot all the rest of these terms, I think. If I just look at the s to the 4 terms, I have minus 1 of them originally, and this expansion must be the same. I have a minus 1 there, and I also have a b there. So this gives me b as 0, and I can continue checking out the s to the 5 terms. There is 0 originally, and here if I multiply out, I get the only way to get to s to the 5 is this term here. So 0 equals a is what I can say from that. So I can clarify that, and then once more just spotting the s terms themselves, I get 0 there. And so expanding this out, the only way to get s terms is this times this, which means c must be 0, and we get that. And again, you can expand this out just to check, but s to the 6 minus s to the 4 plus 3s squared minus 3, and this is correct. But of course this has no more solutions, so the only solutions that I have are these 4 that I originally found up here. It should be noted that the mark scheme found a really nice way of doing that, which is what you say is s to the 8, or sine to the 8, is less than or equal to sine squared, because sine lives between minus 1 and 1, and because when you raise to an even power you're always going to make positives. When you raise things to a higher and higher power between 0 and 1, they get smaller, right? Like 0.5 squared is 0.25, and then squared again, and it gets even smaller than that. So this is always smaller than this, or equal to, but it's only equal to if sine of x is 1, or 0. That's the only time it's equal. Otherwise, every single time it's less than. And you can make exactly the same argument for cos to the 6 as compared to cos squared. So if you take this function and just replace this with a sine squared and this with a cos squared, you're going to be less than or equal to this. But we know this is equal to 1, that's the first thing I wrote down, which means if you want this to be equal to 1, the only possible chance you have of doing that is to make cos and sine just 0 and 1. Otherwise, they're going to be less than this. And that's a really nice justification for why the only solutions I found were when sine was 0 or 1 and cos vice versa. I should have also said or minus 1, I guess, as well. Sorry, I should have also tagged on or minus 1. Apologies. I know that because I found a solution when sine was minus 1, so I should have tagged that on the end. Anyway, this is the very last question, so let's get into it. They like these iterative questions, and you just need to try it until you get enough of a feel for it to figure something out. So f of 1 is 1. When you double n, you just get the same thing you had before, so f of 2, therefore, is just also 1, because when n is 1 here, you get f of 2 equals f of 1, and f of 1 is 1. Now f of 3, you need to, f of 3 is odd, so you need to use n is 1 to get a 3 here, and then f of 1 squared is 1, minus 2 is minus 1. Now f of 4 is just double 2, so that's just the same as 2, according to this rule. F of 5, now 5 is odd, so it's in here. So it's, well, you use n is 2 to make 5. So f of 2 squared, which is 1, minus 2 is minus 1. F of 6 is double 3, so that's just going to be minus 1. 7 is odd, and what we notice is, even if we used, the only things we've got here are 1 and minus 1. Plus or minus 1 squared is 1, take away 2 is minus 1. So any odd number, which you must be making with this rule, is always minus 1. So all of the odd numbers are just minus 1. F of 8 is double 4, so that's just 1. And then again, 9 is odd, so it must be minus 1. 10 is double 5, so that must be minus 1. 11 is odd, so that must be minus 1. 12 is double 6, so that must be minus 1. 13 is odd, so minus 1. 14 is double 7, so minus 1. We're getting a lot of minus 1s here. 15 is odd, so minus 1. And 16 is double 8, which is just plus 1. And hopefully you can see a pattern here, which allows you to circle the answer very quickly. And the pattern I can see is, the function is minus 1 unless you're using a power of 2. Right? Unless you're using a power of 2, then the function is minus 1. So between 1 and 100, how many powers of 2 are there? Well, there are actually 7 of them, because you can use 2 to the 0 to get 1, all the way up to 2 to the 6 to get 64. So there are 7 positive 1s in this list, assuming this pattern continues, and therefore 93 negative 1s. And then 7 minus 93 gives you the answer of minus 86, which seems too convenient to not underline. Now, okay, how do we justify this happens like this? Well, I've already justified that every odd number must be minus 1, right, from this rule, because plus or minus 1 squared is always 1, and then minus 2 is minus 1. Now, what about the even numbers, like, for example, 12? 12 has a 2 in it. So what you can, but because 12 is even, you use this rule. So you halve it until you get to a number that's either even, which you would then halve again until it wasn't even, which therefore must be minus 1, or it's a number that always just has 2's in it, and so you just halve it until you get to 1, in which case it's just 1. And so actually the only numbers that can be 1 are numbers that are only made of 2's, because otherwise you just keep halving them until you run out of 2's in the prime factorization, in which case you end up, like we did with 12, at whatever prime is left, which is going to be minus 1, because odds are always minus 1. And so the only numbers that are 1 are powers of 2. Quite a nice justification, quite a nice question, and yeah, quite a nice paper. I'll see you next time.